Okay, hi everyone. So it's great to start our series Basic Notions seminar now. So as some of you know, but some don't, Basic Notions seminars started maybe 5 years ago, or maybe a little more than that. I'm not sure exactly when. So the original idea was to have like 5-6 talks by locals, by in the department, and covering one area or one field of mathematics at a level that would be understandable to beginning graduate students, good undergraduates, and excellent pros. So now it's a great pleasure to have our own Taylor Brysiewicz, starting the first Basic Notions seminar, Numerical Algebraic Geometry.
All right, thank you very much, and thanks for having me. I'm very excited to tell you a little bit about the background of my work in numerical algebraic geometry. So numerical algebraic geometry has algebraic geometry in the title, and the algebraic and geometric objects algebraic geometers are interested in are polynomial systems, or if you're aware of them, ideals, really. So think you have maybe k polynomials in the polynomial ring. I'll work over the complex numbers today in n variables. And then the geometric point of view of these polynomial systems are the solutions of those polynomial systems. So the zero sets, the common zero sets. And these are called varieties. And we will denote them with this calligraphy V of all the polynomials. And that's going to be a subset of the n-dimensional complex space. So for example, here are two different varieties. The first one is the zero set of x cubed plus xy plus y cubed equals 0. And the second one is the zero set of this linear polynomial. Okay? And their common solutions are the intersection points. So common solutions of polynomials correspond to intersections of varieties. And there's this dictionary that goes back and forth between algebra and geometry, and that's what algebraic geometers study. So one way to study these varieties or these polynomial systems is using a computer, in which case you're in the world of computational algebraic geometry. So for example, if I was a computational algebraic geometer and I wanted to study the common zeros of f and L right here, I could do this in two different ways primarily, either exactly focusing on the polynomial side. So this is the algebraic viewpoint toward computational algebraic geometry, or approximately using numerical methods, and that's the geometric point of view. So if I used a computer algebra system, the best thing I could hope for to understand the ideal generated by f and L would be for a Grosvenor basis. So in this case, I've written the ideal just generated by f, and I've taken its degree. Its degree is 3, which is the same thing as the degree of this polynomial in this case. But the actual definition of degree I'll be using for today is the number of intersection points of the zero set of f with a generic line. And I could compute a Grosvenor basis for the ideal generated by f and L, and out might pop something like this. And that this polynomial has degree 3 is an indication that the degree of this variety is 3. Okay, so that's how I might compute something called the degree using Grosvenor bases in algebraic methods. I could also compute the degree using numerical algebraic geometry, which is the point of today's talk. And this is a much more geometric point of view. Here, we are actually going to intersect this cubic with a generic line and try to compute floating point approximations of all of those intersection points, okay, over the complex numbers. So there, the output might look something like this. So there's 6 lines here, each intersection point has 2 coordinates. Each coordinate is on a line. So there's 3 points of intersection there. And then each line has a real and imaginary part. Okay, so it might be difficult to see for those of you in the back, but you have these real parts, which seem to be reasonable sizes, and then all these imaginary parts are multiplied by like 10 to the negative 36, et cetera. And that's an indication that these are really real solutions that we have. So the imaginary parts are quite small. So how do we solve polynomial systems in the world of numerical algebraic geometry? The standard technique is called homotopy continuation. So somebody hands you a bunch of polynomials, f1 through fn, and they promise you that there are finitely many solutions, perhaps. And you want to find all those solutions. Well, that's a hard task, because somebody just emailed you a really difficult polynomial system. But I'll tell you what an easier task is. For each of those polynomials they gave you, take its degree. So let's say the degree of fi is di. And solve a polynomial system that looks like theirs, but isn't. And it's much easier to solve. So I'm going to cook up my favorite polynomial system to solve, instead of solving the one you sent me via email. And that's going to be the first variable raised to the first degree minus 1, all the way down to the last variable raised to the last degree of fi minus 1. And the solutions to this right-hand polynomial system are clear. The coordinates are each roots of unity. And you have the product of all of these degrees, many solutions. You can just write them down. Now the name of the game is to take those solutions to that mock system and deform them to the solutions that you wanted in the first place. And you do this using a straight line Bézier homotopy. So you just take this convex combination of the polynomial system f and g, called a homotopy. So it's got variables, and it's got this one parameter t. And that parameter is a real parameter that starts at 1 and ends at 0. So when we plug t equals 1 here, we just get g. And when we plug t equals 0 here, we just get f. So this is a family of polynomial systems interpolating between the system you wanted to solve in the first place and the system you were able to solve. So this is geometrically what's going on. So suppose somebody sent me 2 quadratic polynomials in 2 variables, corresponds to the intersection, in this case, of 2 ellipses. Well, I don't want to solve that. That's hard. Let's solve the easy one. X1 squared minus 1 equals 0, x2 squared minus 1 equals 0. So those are just plus or minus 1 for all the solutions. And now as I deform t going from 1 to 0, these are slices of that deformation, and I get this. And the name of the game is, how do you track from the ones you know to the ones you don't? Oh, that's a great question. So there's this fundamental question: what does it even mean to solve a polynomial system? Right? So for a numerical algebraic geometer, it means to provide a very good approximation of the solution. Now, this may be unsatisfying to people who are looking for proofs and things, but we will talk about a method called certification, where you can actually extract mathematical proofs from these approximations. So the polynomial system has common zeros. Right. Finding approximations of those solutions. Yeah. We'll have some more examples. Okay. Great. So here's an example of that process of tracking a path. Okay. So over here on the right, we have this mock system g equals 0. We know all the solutions, and those live in Cn. And those are right up here. And we want to move them over here. So the way to do this numerically is through a predictor-corrector method, where we start here and we take a small time step here, and we try to predict where the solution should be. So we can use Euler's method and use a tangential to this curve. And then what we do is we correct our guess using Newton's method. So you predict, you correct, you predict, you correct, and you march along this path. Okay. There are issues when paths cross, and there are a lot of issues at the end potentially. So things that could happen at the end is you might have a solution fly off to infinity. Its coordinates might just get really, really, really big, in which case you have to just admit that it's going to infinity after it reaches some tolerance and you give up. You could have a solution moving to a positive dimensional component. So if the system you wanted to solve had infinitely many solutions, okay, then you might have a point going to a positive dimensional component. You could have 2 points coming together, or you could have what you're hoping for, which is a screen curve, where it just lands simply at some solution here. Okay. So those are all the situations. And the beginnings of numerical algebraic geometry handled this, this end situation with techniques called end games, which I'm not going to talk about in this lecture. But this process produces all isolated solutions to your f equals 0. There's lots of software that can do this homotopy continuation business. Some of them are listed here. So we have Bertini, PHCPAC, Hom for PS3, Maple has homotopy continuation, numerical algebraic geometry from Macaulay 2 is a native path tracker in Macaulay 2. There's homotopy continuation in Julia. And you'll notice that this task of marching from these known solutions to these a priori unknown solutions, they can be done as individual tasks, right? So if you have, for example, 5 friends, each of you could try to track one of these 5 paths. So you can trivially do this homotopy continuation process in parallel, and then you have to make up a list of all the solutions to each. So you're really taking advantage of multiple processors and parallel computing in numerical algebraic geometry in a way that's more difficult, I would say, for like Grosvenor-Basie's methods. Yeah, so the crossings we're going to guarantee don't happen in a moment. So great. So this homotopy is all a special case of this picture. So I want to spend some time looking at this. This h of x and t, so you got some variables x and some parameters and one parameter t, and you have this convex combination of f and g. That's, to me, just a parametrized polynomial system, where if I specify the value of t, I have finitely many solutions, generically. Well, why just use one t? You can have lots of parameters. So this script f will denote a polynomial system in many variables, many parameters, subject to, if I randomly choose parameters, this should have finitely many solutions. Okay? So that's the setup for this slide. And here's an example of what's going on. So here we have this parameter space downstairs. So it's a cartoon, but think just like a T1 axis and a T2 axis there. And if you pick a parameter value, you'll get a polynomial system with finitely many solutions, and you can solve for those finitely many solutions using the process I described. And let's say you get 6 solutions right there. Okay. Now, homotopy continuation allows me to morph these solutions to the solutions of a parametrized polynomial system over a different parameter. Again, using this path tracking business. Now, as long as I'm staying in a generic locus, there aren't going to be positive dimensional solution sets, and there aren't going to be points crashing together, as long as I avoid a special hypersurface, which is called the discriminant of the problem. So everything in black here, these 2 triangles, the hexagon, and the boundary of that disk, form the discriminant of this cartoon. So along all of these black regions, points either come together, or there's infinitely many solutions, or points go off to infinity. Something other than you have exactly 6 solutions happens. Okay? But generically, with probability 1, you randomly choose a parameter, you're going to have exactly 6 solutions. So that's the setup. And the other nice thing about the discriminant is that over the reals, because this is a real picture, I can only draw real pictures for today, the discriminant is a hypersurface, and so its complement has many connected components, which we'll call regions. Okay. Great. So let's do an example of this. So yes, that's right. The parameter space is complex. I can only draw real pictures. The discriminant is a complex hypersurface over the reals. It's unconnected. And that's a really, so Rasul is asking, if I have a complex hypersurface, its complement should be connected. Right? If I have a real hypersurface, I can have the complement be disconnected. So the discriminant is going to be a complex hypersurface. Its real locus could be a real hypersurface. It might not be. The real locus of a hypersurface. Let me do an example and then we'll see. So solving a univariate quadratic polynomial. Okay. So x squared plus something times x plus something equals 0. My parameter space is T1 and T2. Okay. And the discriminant of this problem is what goes under the square root when you solve the quadratic formula, T1 squared minus 4T2. If I draw the real picture of T1 squared minus 4T2, I get a parabola, which disconnects the real parameter space in T1 and T2. And the components outside are called regions. So there's two real regions here, right? And what happens, if I choose a parameter value, I can solve, and I might have two real solutions, right? So this is now a complex plane, and these are two real solutions on the complex plane. Now I can move around, but if I move toward this discriminant, these two real solutions are going to come together and have multiplicity 2 there, right? And then if I keep moving, they go apart as complex conjugate solutions. Okay. And the nice thing about this discriminant is its complement has components, and by definition, the number of real solutions over each component is the same. Because if you want to switch the number of real solutions as you move along a real parameter space, you better have two real solutions coming together to then become complex conjugate. And two real solutions will come together if and only if your count is wrong, right? So here your generic count is 2, but if you go over the discriminant, the count is 1 with multiplicity 2. Okay. But so now you might have the question of like, well, okay, so how is homotopy continuation going to get me from here to there? That's an issue now. And this is where Rasul's comment really comes in, is that it does not disconnect the space over the complex numbers. So I can take this real one-dimensional path around the discriminant, in which case what's happening is not that these two real solutions come together, become complex conjugates, but rather they just start to rotate into these. And that is the name of the game with homotopy continuation. If you want to solve for things over the reals, is you go up to a complex parameter first, and then you come back down. And with probability 1, you're never touching this discriminant because the complement is connected. And touching the discriminant is exactly when you have path crossings, to answer Jason's question. Okay. Okay, so that was a simple example with two solutions. To convince you of the power of numerical algebraic geometry, there's this wonderful paper by Sascha Timma, Paul Breiting, and Bernd Sturmfels called 3,264 conics in a second. Okay, so there's this classic problem that says, if I give you 5 conics in the plane, how many conics are tangent to all 5? The answer is famously 3,264. And a natural question for a computational algebraic geometer is, can I write all those down? Can I draw them? So here's, for example, 1 red conic, which happens to be tangent to 5 blue conics, 4 ellipses and 1 hyperbola. So what's going on here when they say that they can compute 3,264 conics in a second is that they've pre-computed one of these solution sets. The homotopy continuation process from one parameter value to another takes only a second. That's how fast this works. For this statement to be completely true, you need the word general. So if something is generally true, then you can be in an affine space and you're fine, because the hyperplane at infinity is not general. Okay, great. So a bit of a recap. Somebody wants you to solve a zero-dimensional polynomial system. So they give that to you, and you, as a function, as a numerical algebraic geometer, you output all the solutions, okay? So what do? One, in all of these steps, we embedded the polynomial system we got into a family. Okay, either it's a family just based on this one parameter t, or it's this family of problems about conics. Step two, we solved a generic system in that family that was easy to solve. So in this Bezier homotopy, it was super easy because we constructed it to just have roots of unity as the solutions. But you can choose different families too, in which case step two becomes much harder. And then step three, you go from that generic parameter value to the special one. Here are some choices for step one. So the first one was the Bezier family, where we've already seen this. You just take xi to the power di minus 1. And that's very easy to complete step two for. Instead of just focusing on the degrees of the polynomials you received, you could focus on the monomials of the polynomials you received. And if you restrict to polynomial systems with the same monomials, you get what's called a polyhedral family or a sparse family. And there you solve step two using a polyhedral homotopy. And that's what this citation is. Or you may have a situation where you don't want to do either of these, because the problem description already told you what the parameters are. You don't have to embed it into a family. It's already in a family. But then you would really like to be able to find a member of that family special enough so that you can solve it, and not special enough so that it's general. Or you can use a very distinct solving technique based on an idea of monodromy. Yes? That's a good question. Right. Okay, so the space of all plane conics is a 5-dimensional projective space. So if you write down a plane conic that's something plus something times x plus something times y, you have 6 monomials, right? And this conic is defined up to scaling. So you get a projective space P5 of conics. So now you have a 5-dimensional space of conics. Each tangency condition introduces one equation. And so that cuts your 5-dimensional space down 5 times, and you expect zero dimension of solutions. Okay. Good. Or if you didn't want to do that dimension count, numerical algebraic geometry out of the box will show this for you, which we'll see in a bit. Okay, but first let's talk about monodromy. So this is my favorite concept in numerical algebraic geometry. It's really powerful. And we're going to go back to this picture. So let's say I skipped class when I learned about the quadratic formula, and I Googled it, and I could only find a formula to find one of the roots of a quadratic polynomial. So I only ever knew one, okay? Well, it turns out, as long as I didn't skip the class on numerical algebraic geometry, I'm in the clear, because if I start with just one solution, let's say it's this right blue dot, and I follow this path that I showed before, like up through complex space, okay, and then my right blue dot starts to go a little bit lower in the complex plane. Okay, now I come back to this other point. Now it's this bottom complex conjugate solution. Now let me do a loop. Let me go down here now. Well, now it's over here. And if I pop back to where I started, I have found the other solution. Okay, so loops around the discriminant locus will induce permutations on the solutions. The collection of all permutations is called the monodromy group of this problem. And if that monodromy group is transitive, then by definition, you can apply monodromy group actions to one point and get to any other point. So what's the algorithm? Just start with one solution and keep on applying monodromy loops over and over and over again until you don't find any more solutions. And then guess that you found them all. Okay. So this is a transitive permutation group means you can reach any. So if you have a permutation group acting on a set, you take one element of the set and you can apply group elements to get to any other element of the set. Your group is called transitive. Okay, the domain of the covering space is irreducible as a variety. So there's an output sensitive algorithm. It depends on how many solutions there are. It requires the monodromy group to be transitive. And a big question is there a good stopping criterion? How do I know I found all of them? Maybe I keep on accidentally taking loops not around the discriminant low because I never find anything. I'm like, oh, I guess there's one solution to this quadratic equation. So that's something that could happen. In practice, it doesn't. In practice, you really do find all solutions quite quickly. It also allows you to compute the monodromy groups of parametrized families. And these are interesting in their own right because they encode symmetries of your problem. All right, so this is all well and good. Maybe Taylor has convinced you that numerical algebraic geometry is powerful. You can solve thousands of solutions. You can do it quick. You can do it accurately. But what if you want to prove something? So in what sense did anything you calculate constitute a mathematical proof? Well, here's one sense in which it did. There's a method called Krawcheck's method, which will certifiably give you boxes around your approximate solutions with certificates which guarantee there are unique true solutions within those boxes and distinct unique true solutions within those boxes. How does it work? Suppose we have a univariate cubic polynomial. This is the complex plane again. It has one real solution, two complex conjugate solutions, and those are all red. The ones I've computed are blue, which, by the way, this is a terrible approximation. Okay, but it's illustrative. So the next step is I will put boxes around my approximations. Remember, I do not know what these red dots are. I'm going to put boxes around my approximations. These boxes have exact corners, so rational numbers. They're not floating points anymore. Okay, so these are exact bounding boxes for my approximate solutions, which I am hoping contain true solutions. To verify whether or not they do, I will apply Newton's method to the box, which is an exact operation. And then I will see whether or not the box has contracted. If the box has contracted, that means Newton's operation is a contraction map, which means I have a unique fixed point within this box. That's Banach's fixed point theorem. And fixed points of Newton's methods are solutions. So you're guaranteed to have a unique solution within that box. So you can provably distinguish solutions. You can also decide whether or not they're real or complex. Just make sure your boxes are symmetric over the real axis. If there's only one solution in there, you can't have two complex conjugate solutions in there. And it's also very easy to use. So this is a snippet of Julia code. I say I'm using homotopy continuation. I define two variables. I try to intersect the unit circle with the hyperbola xy equals 1. I solve it. There are 4 paths because these are both degree 2. There are 4 solutions. The time says 11 seconds, but that's compilation overhead. And then I just ask to certify those results. To give you an idea of how quick certification works, those 3264 conics, you can certify those in less than 2 seconds. So you can solve them in 1 second, you can certify them in 2 seconds. This is a one-way street, though. Just because I have certified that I have found a bunch of solutions does not mean I have certified that I have found all of the solutions. And that's a big area of research in numerical algebraic geometry is how do you verify that you found all of the solutions without having some theoretical upper bound, right? So for the conics problem, we know from theory that there are 3,264. And so if I verify that I have found 3,264, I have verified that I found all of them. But right now, there's no way to certify numerically that we found all the solutions. Okay, so recap. The intermission of the talk. We have learned that we can find the approximate solutions to polynomial systems when we have finitely many solutions using homotopy continuation. It's fast, it's trivially parallelizable, and we can certify these results. Not only that, we're allowed to move around this parameter space fairly efficiently. So if I'm an algebraic geometer, one thing that this talk has lacked for me so far is how do I handle positive dimensional varieties, right? So 0-dimensional varieties are all well and good for the enumerative geometry, but maybe I'm interested in larger sets. And numerical algebraic geometry has an answer for that as well. First, let me just point out that a variety is any solution set to a bunch of polynomial equations for me. And they can be 0-dimensional, like these 4 points. They can be positive dimensional, like the solution set to x squared plus y squared minus 1 equals 0. They can have different components. So here, you have a circle and a parabola. Both are varieties in their own right. And you could have a polynomial system whose 0 set is the union of these two. Just multiply their equations together. And similarly, you can cook up polynomial systems which are who have solutions which are the union of any varieties, finitely many varieties. Okay, so they might not even have the same dimension. So these are the kind of these 4 situations are some of the situations that we'd like to handle. We can handle more, but let's just talk about these. As alluded to in the first slide, the degree of a variety is the number of intersection points over the complex numbers with a generic linear space of the dimension which would cause me to expect finitely many solutions. Okay, so complementary dimension is what we call this. And the main data type of numerical algebraic geometry is something called a witness set. So a witness set represents a variety, an irreducible variety, by a triple. The first is a polynomial system f, for which your variety is a component of the 0 set of f. The second is a linear space of complementary dimension. And the third part of this triple is a collection of approximations of points of intersection between x and this linear space. For example, these are depictions of witness sets. So on the left, we have a curve in the plane. So its codimension is 1. So a complementary linear space has dimension 1. In other words, if I intersect this quartic curve with a line, I would expect finitely many points, namely 4 points, which is what makes it a quartic. And if I find numerical solutions, numerical approximations of these 4 points, and I have the equations which cut out the quartic and equations which cut out the line, those 3 pieces of information together give me something called a witness set. Okay. And then this is my awful cartoon of a twisted cubic intersected with a hyperplane. So this is a space curve. So it's a curve in space. And I slice it with a hyperplane because that's the linear space of complementary dimension. And I get 3 points, which is why it's called a cubic, because its degree is 3. Okay, so this is a witness set. And at first glance, it might be a little bit mysterious that you can do much with this object. But you got to remember that you don't just have this triple. With the power of numerical algebraic geometry, you also have a way to move the linear space around and track the solutions. You can also think about the computation of a witness set itself as one of these parametrized polynomial systems with finitely many solutions. Right? Here, our solution space is just some irreducible variety. And then the parameter space this time is just the space of all linear spaces of complementary dimension. Of course, generically, I'll have finitely many solutions. Generically, I'll have the same number of solutions, the degree of the variety. And I have this incidence variety I, which collects all points inside linear intersections. So we call this type of parametrized polynomial system maybe the degree problem of the variety. Why? Because if you solve it, you've computed the degree of your variety. And here, you compute all 4 solutions to an intersection with a line of this quartic. You can then move that line around in the parameter space, and that moves the geometric picture on the right, the linear space around, and you track those solutions around. Okay. So why is this helpful? Well, it's kind of the basis of what witness sets can do. So what does a witness set tell you? So the first thing it tells you immediately is what is the dimension of the variety and what is the degree of the variety. Right? Because you know the dimension of this linear space because you can do linear algebra. So you know its complementary dimension to the variety, and so you know the dimension of the variety. Kind of trivially, you know the dimension of the variety. It's baked into the data structure. You also know the degree of the variety, also baked into the data structure. It's the number of points in this set S of approximate solutions. The degree of an irreducible variety is the number of intersection points with a generic linear space of complementary dimension. Yeah, we could talk after. I'm not sure off the top of my head. It's the degree of this as a branched cover from the instance variety down to this, but that's kind of immediate, I guess. So what can we do? So the first thing we can do is we can sample random points on our variety. Just move your linear space to a random linear space and pluck off one of the intersection points. You have a generic point on your variety. You can do membership on your variety. If I have a witness set for, let's say, this torus, and I have a point, and I want to know whether or not this point is on the torus. Okay, so here's my witness set that I've computed. Here's the point I want to test whether or not is on the torus. I'll just move this linear space to any line through that point and see if one of your witness points goes there. And then you'll know whether or not that point is contained in your space. You can do containment of varieties. Okay, so here we have a circle and it's contained in the torus, and we want to verify whether or not this is the case. Well, as long as I have a witness set for this circle, I can choose a generic point on it. And then I can check if that generic point is on the torus. A generic point on this circle is going to be on the torus only if the circle is a subset of the torus. But the key thing that I think really hammers home how powerful numerical algebraic geometry is this picture. So if you've spent any time working with Grosvenor bases or elimination theory, you know that the problem of elimination is hard. If I have some variety and I know its equations and I project it, it's hard to find equations of the projection. The way I know how to do this involves Grosvenor bases, but it is a trivial operation if you have a witness set. Okay, so here is a space curve cartoon, and suppose I have some witness set for it, which is not this linear space because this is not a generic linear space. So suppose I have a different one. I can project the curve. So theoretically, I have some curve downstairs, and I want a witness set for it. All I have to do is tilt my witness set to be vertical with respect to the projection, and then project all my witness points. So numerical algebraic geometry is the geometric viewpoint of computational algebraic geometry. And so you would expect it to perform very well under geometric operations like a projection. Algebraically, this is very hard. So I spend a lot of time solving this degree problem for various varieties and lots of variables and stuff like this. And my preferred way of doing this is through monodromy. already discussed how this degree problem is one of these parametrized polynomial systems. And I've already discussed how monodromy solving works. You just keep on running these loops. The thing with running monodromy on the witness problem for a variety is you're never going to get a point that's on a component other than where you started. Okay. So for example, let's say my variety is the intersection of that blue quartic and a circle. And I start and I try to compute the intersection of the blue quartic and the circle, which I don't know is a blue quartic and a circle. I just have some equations, right? With a linear slice. If I start with this blue point and do monodromy, I could get this, or this blue point, but I'll never jump over to this red point. Because doing so would require me to pass through the intersection of the blue and the red curve, which will always be in the discriminant of this problem. Right? So in other words, the monodromy group of this witness problem would be the full symmetric group on these 4 points times the full symmetric group on these 2 points. Okay, but the nice thing is that, I mentioned this monodromy computation, you want a stopping criterion. You want some way to verify you have found all the solutions. And when you're doing a witness set computation, there's this really, really cool test called the trace test, which will tell you whether or not you have found all the solutions. So let's say that I've started with this solution, I've run monodromy, and I found these other 3 blue solutions. And I want to know, have I found all of the solutions on a component of this variety? Here's the trick. Move to 2 parallel linear slices. Compute the average coordinate-wise of your blue points. So that's this x here. And see if that average travels in a line. If it travels in a line, you found all the points. And if you haven't found all the points, it will not travel in a line. Sorry? Why? So this all boils down to if you have a univariate polynomial and you take the sum or the average of all of its roots, then that is the second highest coordinate of the univariate polynomial. That is what it boils down to. It's all the way back to Newton. Okay? So that fact plus elimination theory will give you this theorem. Okay. And this is a great way to find all of the components. What do? You solve for all the intersection points of this line with the union of the blue curve and the red curve. But you don't do it using monodromy because you won't find everything using monodromy. You do it via like a Bezout thing or something like that. You will find them all that way. And then you perform monodromy and you see which points start to permute with each other. You'll notice only 4 are permuting and 2 are permuting. And that gives you the components. So that is called the monodromy breakup algorithm. So after you solve for what's called a witness superset, which means all the intersection points, then you do monodromy and you partition these points based on their orbits under the monodromy group. All right, but this last description of finding components, you might notice, oh, well, that only works if they're all the same dimension, right? So how do you do it if you have components of different dimension? And there are papers on this, and I'm not going to go over it, but it's called the numerical irreducible decomposition. Basically, you find an intersection with each of these dimensional linear spaces, and then you do that monodromy breakup on each one of those solution sets. So here's kind of some pseudocode for that. And here's Macaulay 2 finding the components of an algebraic variety. So I just typed in some equations, said numerical irreducible decomposition, please. And Macaulay says, well, there's 2 components in dimension 1, so it's got 2 curves, each has degree 5, and then there's a surface of degree 2. Completely. It's a purely geometric algorithm, just based on this homotopy continuation gram, yeah. Is it a lot faster? Well, it depends on your system. If you want to compute a Grosvenor basis, but you're working with floating points, you're going to have trouble, for example. But if you're working with a very, very structured system, you might compute the Grosvenor basis very quick, particularly if your input was a Grosvenor basis. So, yeah, generally, the rule of thumb is that you're going to be faster here, but you might have some numerical errors. What else can I say about the comparison? Numerical methods scale very well with dimension and poorly with the degree of the input polynomials, whereas Grosvenor basis methods tend to be the opposite, in my experience. Okay. So in the last 4 minutes or so, let me just talk a little bit about an area of this world that I'm exploring right now involving hill climbing algorithms. So suppose we have one of these parametrized polynomial systems again. We have lots of solutions. Let's say those blue ones are real, and those red and pink ones are complex conjugate solutions. And I'm in some region of this discriminant, and let's say I got 54 real solutions. Okay. My goal is to find as many real solutions as I can. So the question is, how can I move throughout this parameter space in a way that will optimize for the number of real solutions? And this is particularly important if you're dealing with polynomial systems coming from applications where only the real solutions are relevant. Well, an idea that goes back to Dietmeier, which is this citation, is to sample randomly many parameter values near the one you've computed. Use homotopy continuation to compute all of those. Remember, for 3264, it only takes a second, so that should be pretty fast. And then, first of all, see if you accidentally sampled something in a different chamber that has more real solutions. If so, move over there and do it again. But in case that you stayed in this chamber, what you want to do is you want to choose the new parameter to be the one where the complex conjugate solutions have gotten closer, right? Because how do you get new real solutions? When the complex conjugate solutions come together and then become real. So this gives you a way to stochastically decide how to move in your parameter space to try to optimize greedily for more real solutions. And so here we see two complex conjugate solutions coming together and then splitting up into real solutions up there. So that's the cartoon. So the hill climbing is that you have this that you have some function you're trying to optimize. In this case, number of real solutions, which is more like a series of plateaus over the space, and you're trying to climb the plateaus. So you're really lucky if you have a continuous function, but for this specific problem, you kind of have like curvy plateaus where you do have higher points, like more preferred points within a chamber, but that's locally based on these complex conjugate solutions coming together. So the hill is the value of the function you're trying to optimize, not this. This is just the trick you use to avoid having to cross the discriminant in your homotopy continuation. Yeah. So, 2 years ago, myself and 2 others, we tried to find as many real solutions as possible to 55 different problems up to symmetry. Okay, so these numbers are the degrees of each of those problems. So the 128 corresponds to some problem with 128 solutions. In fact, it corresponds to this problem. And this problem asks, how many quadric surfaces in 3 space are tangent to 5 lines, go through 2 points, and are tangent to 2 planes. Okay, so these are like linear versions of this conic problem. So these date back to Schubert. And our goal was to show that each of these have specific parameter values, i.e. points, lines, and planes, for which every solution is real. Okay, so in other words, we wanted to show that all of these were totally real. Now, people have done this in previous work for single problems, you know, and these were hallmarks of the field of numerical algebraic geometry. And so we tried to do it for 55 problems, and for everything but the boxed problems, we found completely real solution sets. So we ran this for several days on a computer, this hill climbing algorithm, and for everything but these, we have found completely real solution sets. For these ones, we were only able to find these amounts. So we're like off by 2 for this 112 to 110, off by 6, not off by much. We still found lots of real solutions, but the goal was to find all of them. So it wasn't a complete solution, and maybe you can't have all real solutions to these. But if you're interested in working on a problem, having some fun with numerical algebraic geometry, you could try taking a look at these. Graham. So Graham asked, is there some way to avoid suboptimal maxima in the hill climbing? So local maxima, which are not global maxima. I haven't found a way. So instead, I just repeat this over and over again with new starting points. I keep on climbing as high as I can. Or sometimes if I've decided that I've gone as high as I can locally, I'll just have this like extra routine that just randomly shoots it around and does it all over again. And this was all automated on the computers at the Max Planck Institute, kind of in an ad hoc fashion for this problem. But yeah. So thanks a lot. Here are some pictures to inspire questions.